What if you could custom build the very silicon your applications run on, like on demand, right there in the cloud? Imagine the power, the bespoke speed, the optimization, just at your
It
fingertips.
sounds almost futuristic, doesn't it?
It really does. Okay, let's unpack this. Welcome, everyone, to a deep dive into FPGA as a service, or FEAS, a truly groundbreaking shift in high-performance computing, I think.
Definitely.
Our mission today is really to pull back the curtain on this, well, pretty specialized compute offering. We're going to explore its unique advantages, how the big cloud providers are doing it, and, what it actually means for the future of processing power for you.
hmm
We're aiming to give you a shortcut, really, to getting well-informed on this fascinating area. So get ready to understand the invisible engines behind some of the absolute fastest, most critical computing tasks out there.
It's a field that's been quietly evolving for a while, and its appearance as a cloud service is, well, it's fundamentally changing how lots of industries approach their toughest workloads.
So to really get the as-a-service part, we first need to understand the FPGA itself, right? What in the world are these things? They're definitely not your standard CPU or GPU.
Not at all, no. FPGAs, field programmable gate arrays, they're a unique class of chip. So unlike your typical processors with fixed architectures running software instructions, an FPGA is literally reconfigurable after it's made.
Okay.
Imagine a chip like a blank canvas, filled with millions of these tiny configurable logic blocks and programmable connections between them.
Right?
This lets developers essentially, well, draw or define custom logic circuits that then execute natively right in the silicon itself.
Ah.
And the real insight here, I think, is that this reconfigurability makes FPGAs kind of a strategic bridge in the whole compute hierarchy. They sit neatly between the flexibility of software programmable CPUs and GPUs and the rigid but super efficient world of ASICs, application-specific integrated circuits.
So it's not just running code. You're actually building the specific hardware circuit for your task.
Yeah.
That feels like the aha moment for a lot of people, realizing it's this blank silicon you can truly customize.
Exactly.
What does that actually mean for performance in the real world? I keep hearing about true hardware parallelism and like ultra-low latency.
Precisely. And those core advantages come straight from that unique architecture. When we talk about true hardware parallelism, we mean different parts of your task don't have to fight for the same resources. Each independent operation can get its own dedicated, physically separate bit of the chip and just run on its own. This allows for massive, really fine-grained parallel processing. It's quite different from a CPU's sequential nature or even a GPU's SIMD parallelism, which is still kind of applying one instruction to lots of data, just within a more fixed structure.
Okay.
And this hardwired direct logic also gives you that ultra-low latency. There's no instruction fetch, no decode stages.
Wow.
The logic is baked right into the silicon. That lets you hit sub-microsecond speeds. For certain really intensive tasks, this means huge speed improvements and often much better energy efficiency compared to even GPUs.
So the value proposition here is basically bypassing all that software overhead.
Correct.
Just raw, direct silicon execution. That's a massive difference.
It really is.
Now, despite all that power and efficiency, FPGAs haven't traditionally been, everywhere. If they're so good, why aren't they in every server?
Yeah.
It sounds like there must have been some pretty big hurdles to actually using them.
Oh, historically, absolutely. The traditional barriers were, frankly, formidable. First off, the initial capital investment for doing FPGA development on-premise was just prohibitive.
Right.
You're talking high costs for the chips themselves, specialized test gear, and incredibly expensive software development tools. And beyond the cost, the development cycle itself was notoriously complex and slow. You needed deep skills in hardware description languages, things like VHDL or Verilog. These aren't really software programs. They're code that describes hardware circuits.
Very different skill set.
Totally different. I remember early projects, you could spend days debugging a single logic gate connection. It's a stark reminder of how tough it was before the cloud simplified things.
Yeah.
Plus, manual tasks like design partitioning, splitting a big design across multiple FPGAs were just tedious and really prone to errors. And debugging hardware, fundamentally harder than software. Finally, on-prem systems just didn't scale easily. Adding more capacity meant long lead times and more big investments.
Okay, so if those were the big roadblocks, how does putting FPGAs in the cloud as a service fundamentally change that picture?
Well, cloud-based FACE tackles pretty much every single one of those traditional hurdles head-on.
How so?
By offering FPGAs as this remote, on-demand service, the cloud providers just wipe out the need for any upfront capital investment. Developers can get access to powerful FPGA resources instantly, and crucially, pay only for what they use.
Pay as you go.
Yeah. Exactly.
No way.
Which is incredibly cost-effective, both for trying things out and for running production workloads. The cloud also gives you instant and, practically unlimited scalability. You can spin up as many instances as you need and then spin them down just as fast.
Right.
This whole model just drastically cuts down the time to market by getting rid of all those procurement and setup headaches.
Makes sense. Now, one thing that sometimes trips people up is that acronym FAS. It actually pops up twice in the cloud world, doesn't it?
Mm-hmm.
And it's probably important we clarify which one we mean today.
It certainly is, and it's a critical distinction. Yeah, most often FAE means function as a service. That's your serverless compute model, event-driven code execution without managing servers, Lambda, Azure functions, that sort of thing.
Right, the serverless code stuff.
But our focus today is FPGA as a service, which is about providing these programmable logic devices, the FPGAs themselves, as a remote service for custom hardware development. And then there's even a third slight variation, FPGA for a service. That's where you're not getting the raw FPGA to program yourself, but rather a pre-built hardware-accelerated application, like maybe a specialized video transcoder that uses FPGAs under the hood.
Got it. So raw hardware access versus a pre-built accelerated service.
Exactly. But what's kind of fascinating is that even though the acronym is shared, both types of phase function and FPGA point towards this broader serverless philosophy, right? Abstracting away the underlying complexity to make powerful tech accessible to more people.
It's almost like the cloud world enjoys keeping us on our toes with its acronyms sometimes, isn't it?
Seems that way sometimes.
It really is about making cutting-edge tech accessible, though. And speaking of accessibility, two of the cloud giants have really led the charge here. AWS with their F1 instances and Azure with their NP series. How do these two sort of pioneering offerings stack up?
Right, so AWS F1 instances were definitely among the first big public offerings in this space. They were designed to accelerate all sorts of workloads, from genomics to machine learning inference, financial modeling. Architecturally, the F1 instances use what's called a PCI-attached coprocessor model. Basically, each FPGA is connected to the host server CPU over a high-speed PCIe bus, and it acts like a helper, a subordinate worker to the main CPU.
Okay.
AWS F1 uses powerful Z-Links FPGA, specifically the Vertex UltraScale plus VU9P at launch, offering millions of these reconfigurable logic elements, thousands of dedicated math blocks or DSP engines, and quite a bit of on-chip memory, plus its own dedicated DDR4 memory.
And what seems crucial here is how AWS really tried to democratize access, right? Moving beyond just handing over the raw hardware.
Exactly. That was key. A core part of the F1 offering is the MTGA Developer AMI. That's a pre-configured machine image with the whole development environment ready to go.
Okay, so it saves setup time.
Big time. It includes the Xilinx tools, Vivado and Vitis, plus AWS's own Hardware Development Kit, HDK, and Software Development Kit, SDK. Now, the HDK provides this really important piece called the FPGA shell.
The shell, what's that do?
It's basically a predefined block of logic that handles all the complex stuff of talking between the FPGA and the host system, managing the PCIe interface, memory access, that sort of thing. It abstracts away a lot of the low-level plumbing.
So developers can just focus on their own logic.
Precisely. They work within that shell, focusing purely on their application-specific acceleration kernel. And maybe the biggest democratizing factor was high-level synthesis, or HLS.
HLS.
Yeah, this allows developers to write their acceleration kernels not in those complex HDLs like VHDL or Verilog, but in more familiar languages like C, C++, or OpenCL. The tools then synthesize that high-level code down into a hardware configuration.
Wow, okay. That's huge.
It is. The genius of HLS isn't just technical, it's strategic. It potentially expands the pool of people who can innovate with FPGAs from maybe a few thousand specialized hardware engineers to literally millions of software developers. That fundamentally changes who can build with this powerful hardware.
So it's not just for the hardcore hardware folks anymore. That really opens things up. What are some of the big use cases we've actually seen emerge on AWS F1?
We've seen significant adoption in genomics acceleration. Illumina's Dragon BioIT platform, for instance, uses F1 for ultra-fast secondary analysis of genomic data. The parallelism is just perfect for that kind of massive data crunching.
Makes sense.
Another huge area is high-frequency trading, HFT. FPGAs can process market data and react to events in sub-microsecond timeframes, which is way faster than any software-only solution could manage.
Right. Speed is everything there.
Absolutely. And they're also used in high-performance computing, scientific simulations, and media processing, like real-time live video transcoding at scale.
Okay, now let's pivot to Azure's NP series. What's under the hood there, and how does their approach maybe differ?
Azure's NP series VMs pair Intel Xeon CPUs with AMD Alveo FPGAs, specifically the U250 initially. So different silicon vendors, but offering comparable levels of logic, DSP blocks, and memory to what AWS provides. They also offer various VM sizes, giving you flexibility in CPU cores, memory, and the number of FPGAs attached.
What I find really interesting about Azure's story is its origin, especially that Smart NIC heritage from Project Catapult way back in 2010. It feels like maybe a different strategic motivation behind it.
I think that's a very insightful point. If you connect the dots, Azure's whole approach to FPGAs feels deeply rooted in this infrastructure-first philosophy. They were building from the inside out.
How so?
Well, as early as 2010, Microsoft saw the potential for FPGAs to accelerate their own core cloud services, starting with web search on Bing. By 2015, they had FPGAs deployed at scale across Azure's public cloud infrastructure, mainly acting as smart NICs.
Smart NIC, smart network interface cards.
Exactly. They became the default hardware for implementing virtual network functions through their AxleNet program. This strategy let Azure offload critical networking tasks like encryption, firewalling, virtual switching from the host server's CPU directly onto the FPGA.
Freeing up the main CPU.
Precisely, preserving those valuable host CPU cores entirely for customer workloads. So this is a fundamental difference in origin story, right? AWS F1 was launched as a direct product for external developers. Azure's NT series is more like the public-facing result of this decade-long internal infrastructure investment that they gradually opened up.
Interesting. So build for themselves first, then offer to customers.
Pretty much. And for developers using NP series, this often translates into things like simplified deployment through pre-configured marketplace images, with Azure handling more of the underlying integration. They've also made a point of showing vendor independence, demonstrating how code could potentially be ported between different FPGA types like Xilinx and Ultra and Intel.
So, okay, high level. Both use that PCIe attached model, VMs talking to FPGAs using chips from the big players like Xilinx and AMD Altera. But maybe the strategic value or the ecosystem fit differs depending on whether you're already heavily invested in Microsoft Azure or the AWS ecosystem.
That's a fair summary. Your existing cloud footprint and specific workload needs definitely play a big role in platform choice.
And pricing. Is it similar?
Broadly, yes. Both AWS F1 and Azure NP series primarily use an on-demand pay-per-hour model. This keeps that barrier low, no huge upfront costs, which is central to the whole as-a-service idea.
Right. So FPGAs clearly have their niche, a powerful one, but they're not the only game in town for acceleration, are they? Where do they fit in the bigger picture compared to, say, GPUs or even TPUs?
That's a really important question. It's definitely not a one-size-fits-all situation. It's all about picking the right tool for the specific job. So GPUs, graphics processing units, they're kind of the general-purpose parallel workhorses, right? Fantastic for massive, highly parallel computations. Think AI and machine learning training, big scientific simulations, video rendering. They've got a very mature software ecosystem, CUDA especially, and they're incredibly versatile for a wide range of tasks that benefit from that kind of parallel throughput.
The go-to for many parallel jobs.
Exactly. Then you have TPUs, tensor processing units. These are Google's custom ASICs, application-specific integrated circuits. They are purpose-built, designed from the ground up, specifically for machine learning. They absolutely excel at the large matrix multiplications that are fundamental to neural networks. For those specific narrow workloads, they offer pretty much unparalleled performance per watt.
Hyper-specialized for AI.
Right. Very, very good at one specific important thing.
So if GPUs are the versatile parallel workers and TPUs are the AI specialists, where do FPGAs slot in? What's their unique sweet spot?
FPGAs offer this really interesting middle path. Their killer advantage is that reconfigurability combined with true hardware parallelism that we talked about earlier.
Right.
This combination enables that ultra-low latency and often very high energy efficiency for quite specific, sometimes highly specialized tasks. Think back to that high-frequency trading example, microseconds literally count. Or real-time signal processing, complex network packet processing, maybe certain types of encryption or compression where you need deterministic, super fast responses.
So latency-sensitive custom logic type stuff.
Exactly. They shine when you need to perfectly tailor the hardware to your algorithm, especially if that algorithm might change or evolve over time, because you can just reconfigure the FPGA. You can't do that with an ASIC like a TPU.
So choosing the right accelerator is entirely a workload-centric decision then, it sounds like.
Absolutely. The framework for deciding has to start with analyzing your workload's specific characteristics. Does it have massive data parallelism? Are there incredibly strict sub-millisecond latency requirements? Is raw throughput the main goal? Does it heavily rely on those big matrix operations core to deep learning?
Right.
Aligning those needs with the strengths of the accelerator, GPU, TPU, or FPGA, is just crucial for getting the best performance and efficiency. There's really no single best accelerator overall, only the best one for your particular problem.
Makes sense. Now, even with the hyperscalers like AWS and Azure making FPGAs way more accessible than they used to be,
Yeah.
that development process, especially with HLS, can still feel pretty involved, right?
Right.
Are there other players emerging to maybe simplify things even further?
Yes, absolutely. That's a developing area. We're definitely seeing the rise of third-party abstraction providers who are essentially building a value-add layer on top of the raw cloud infrastructure.
Like who? What do they do?
Well, companies like Plunify Cloud, for instance, they offer these tailored cloud environments specifically designed for FPGA designers. Their whole value proposition is handling the tricky infrastructure setup, the security configurations, allowing developers to just focus purely on their hardware design and compilation flow.
Okay, simplifying the environment.
Exactly. They even do things like offer transparent cloud credits and per minute pricing, trying to make the costs clearer and more manageable than just dealing directly with the hyperscaler billing sometimes.
Right. And what about managing these FPGA resources once you have them deployed, especially at scale?
Yeah, that's another area. Companies like InXL are tackling that. They provide more of an enterprise-focused software stack for managing and deploying FPGA infrastructure across potentially many instances or even different clouds. They often leverage modern orchestration frameworks like Kubernetes.
Ah, bringing FPGAs into the DevOps world. Sort of.
Kind of, yeah. Making them manageable just like any other compute resource through a unified dashboard or API, abstracting away a lot of the underlying FPGA-specific complexity.
So what does this all really point to for the future? It almost sounds like we're heading towards a more layered phase ecosystem. Maybe hyperscalers provide the base hardware, and these specialized companies add tools and platforms on top.
I think you're spot on. That seems to be the trend. These providers are building that critical layer of abstraction. It suggests a future where, yeah, the hyperscalers provide the foundational silicon as service, and then specialized companies offer more refined managed platforms, specific tool chains, maybe even pre-built application frameworks on top of that hardware.
Which should hopefully make it even easier for more developers to actually tap into this power, right?
That's the goal. Further simplifying the experience and broadening adoption.
Okay, this all sounds incredibly promising for performance and customization, but whenever you talk about shared resources in the cloud, especially shared silicon, my security senses start tingling. What unique challenges or risks does Cloud Phase introduce compared to, say, just running VMs?
That's a really critical point, and you're right to raise it. This does raise an important question. The multi-tenant nature of cloud FPGAs, while cost-effective, introduces a pretty profound security risk that's fundamentally different from software-isolated VMs.
Oh, so what's the difference?
Well, unlike VMs where the hypervisor provides strong isolation boundaries in software, multi-tenant FPGAs often involve multiple users literally sharing the same physical piece of silicon. And crucially, they often share underlying infrastructure, like the power distribution network, the PDN.
The power lines on the chip itself?
Exactly. And this shared physical infrastructure creates vulnerabilities to some pretty sophisticated hardware-level attacks that just don't really exist in the same way in traditional VM-based cloud models.
Yeah. Okay, you've got my attention. What kinds of attacks are we talking about here? Can you give us some concrete examples of how this shared physical layer becomes a problem?
Sure. A primary threat is what's called a remote side channel attack. Imagine a malicious tenant programs a circuit on their part of the shared FPGA fabric, but this circuit isn't doing useful work. It's designed to act like a tiny sensitive sensor.
A sensor on the chip.
Effectively, yes. This sensor can monitor minute voltage fluctuations on that shared PDN. Now, these tiny power fluctuations are caused by the activity of a victim circuit running elsewhere on the same chip, perhaps doing something sensitive like an encryption calculation.
Um,
Right. The attacker records these power fluctuations and can then use statistical analysis to infer sensitive data being processed by the victim, potentially even extracting things like cryptographic keys. And this isn't just theoretical. Researchers have demonstrated these kinds of remote power analysis attacks on commercial cloud FPGA platforms like AWS F1.
wow. Okay, that's concerning. Are there other types?
Yes, there's also a more aggressive variant called a fault injection attack. Here, a malicious user might intentionally program their part of the FPGA to draw power very aggressively, trying to overload the shared power supply.
Why would they do that?
This can cause transient voltage glitches across the chip. These glitches can lead to timing violations in the victim's circuit, causing errors in computation. And sometimes these induced errors can actually be exploited to compromise cryptographic secrets or disrupt critical operations.
So this isn't like a software bug you can just patch, is it?
Exactly, that's the crucial point. This is a fundamental hardware vulnerability stemming directly from sharing physical resources. It's not something you fix with a simple software update.
I see. So this really is a deep-seated issue, not just something at the application layer. It requires a different kind of thinking.
Absolutely. It means anyone adopting FAS, especially in multi-tenant scenarios, needs to approach security from first principles. You have to understand this risk. Mitigation requires either opting for dedicated hardware isolation, where you get the whole FPGA chip to yourself, which is usually more expensive, or relying on sophisticated hardware-level countermeasures that the cloud provider might build into the platform itself to detect or prevent these attacks. It's a really serious consideration that needs a mature strategy.
Definitely something to keep front of mind. Okay, what about latency? We celebrated FPGAs earlier for their ultra-low latency, but how does putting them in the cloud, potentially far away, affect that key advantage?
That's another important practical consideration. While the FPGA itself offers that fantastic sub-microsecond latency for logic running right there on the silicon, the cloud deployment model can introduce bottlenecks elsewhere.
Like network latency.
Exactly. The physical distance between your application and the data center hosting the FPGA and the network path involved can add significant round-trip latency. For some applications, like that high-frequency trading example, even a few extra milliseconds of network delay can completely negate the FPGA's speed advantage.
Right, the whole system matters.
Precisely. And the common PCI attached model also creates a dependency on the host CPU. Data often has to travel from the network to the host CPU's memory, then across the PCIe bus to the FPGA and back again. Each of those hops adds overhead.
So are people working on ways around that, different architectures?
Yes, there's research and some emerging architectural shifts. For example, IBM had a research system called Cloud FPGA, which proposed disaggregating the FPGAs. Instead of being tethered to a specific host server via PCIe, the FPGAs would be more like independent, self-managed network peers connected directly to the data center network fabric.
Ah, cutting out the middleman CPU for data transfer.
Kind of, yeah. Reducing those bottlenecks, getting the FPGA closer to the data source and destination, and making the number of FPGAs you can use independent of the number of host servers. It's about optimizing that entire data path, not just the computation on the chip itself.
This has been an incredibly insightful deep dive into what's clearly a complex but really powerful technology. For you listening out there, maybe considering phase for your own projects, what's a practical way to think about making an informed decision, a sort of framework?
Yeah, I think a clear workload-centric analysis is absolutely essential. 3 key steps, maybe. First, really analyze your application. Is it truly FPGA-friendly? Does it have that inherent fine-grained parallelism? Does it have absolutely strict latency needs? Or maybe critical performance per watt requirements that CPUs or even GPUs just can't meet efficiently? Don't use an FPGA just because it sounds cool.
Right, make sure it's the right fit.
Second, carefully select your cloud platform. Think about your existing enterprise cloud footprint if you're heavily Microsoft-based. Azure's integration might be compelling. If you're already deep in AWS, M1 is the natural path. Also, look closely at the availability and maturity of those high-level synthesis tools if you plan to use C++ or OpenCL, as that can significantly impact your development speed and talent pool.
Okay, workload fit, platform choice. What's third?
And third, Given those unique security vulnerabilities we just discussed, you must implement a robust security mitigation strategy from day one. Understand the risks of multi-tenancy. This might mean budgeting for dedicated instances if possible for sensitive workloads, or carefully evaluating and leveraging any hardware-level countermeasures the cloud provider offers. Don't treat security as an afterthought here.
Workload platform security. Got it.
Yeah.
So looking a bit further out now, crystal ball time. What does the future hold for this reconfigurable cloud? Where are things generally headed?
Well, the Faceless ecosystem is definitely still maturing, but we can see several key trends shaping up. On the hardware side, expect continued evolution. We're likely moving towards more chiplet-based designs.
Yes, Jakes.
Yeah, co-packaging CPUs, FPGAs, maybe even specialized AI accelerators onto a single package, sometimes even a single piece of silicon, using advanced packaging techniques. These components will be physically much closer, talking over high-speed interconnects.
Reducing latency even further.
Exactly. Tighter integration between hardware and software. On the software and abstraction side, we'll see continued development, especially things like AI-specific overlays. These are like pre-configured logic blocks optimized for common AI operations, making FPGAs easier for software developers to use for AI inference tasks without deep hardware knowledge.
Making them more application-specific, but still flexible.
Sort of, yeah. And finally, there's active research into true FPGA virtualization, the ability to securely partition a single FPGA fabric among multiple users, each with their own isolated slice.
True multi-tenancy on one chip.
That's the goal. But it's important to acknowledge this will likely amplify those security challenges we talked about. So developing secure multi-tenant hardware architectures is going to be a really critical area of ongoing research and innovation.
Wow. Okay. We've certainly journeyed from the basic idea of reconfigurable hardware all the way to its cloud integration, how the big players are enabling it, the challenges, and even a peek into what's next. It's clear that Face has really matured into a powerful, albeit specialized tool for certain very demanding workloads.
Absolutely. And while the hyperscalers have done a massive job in democratizing access, unlocking its full value really requires understanding both its unique, sometimes unparalleled benefits and its inherent hardware-level risks and architectural dependencies. It's an incredibly powerful tool, but definitely one that demands an informed strategic approach.
The reconfigurable cloud is definitely here, and it's clearly still evolving rapidly. So considering everything we've discussed today, the custom logic, the ultra-low latency, the energy efficiency, even those unique security considerations, here's something for you to think about. What problem, maybe one you're facing right now, could you imagine solving with dedicated programmable hardware available on demand in the cloud?